Hannes here, which is pretty nice. He's from Meta, and I guess did the last of the Rumor and first of the Rumor. And yeah, I'm sure he has some nice knowledge also beyond those papers, and can get some yeah nice overview in general and those papers. So thanks.
Yeah, cool. Thanks for the intro, Hannes and Felix. Thanks for inviting me. This is fun. Um, so I'm Brandon Wood. I'm a research scientist at FAIR. My talk is exploring the frontier of universal machine learning potentials for chemistry, and I'll focus a little bit more on OML 25 and UMA just because they're quite recent. Okay, this is our FAIR chemistry team. So there's about 14 or 15 of us, and we're primarily based out of San Francisco. I think probably the most common question we get is, why does Meta care about chemistry? Why does Meta have a chemistry team? So uh, since we've been around probably 2019, we've been using AI to discover and design materials and now molecules for applications ranging from climate change to AR glasses. And um, the closest connection to business is the AR glasses. So looking at trying to discover new display materials. Additionally, a lot of the stuff that we've done on climate change or renewable energy storage, there is a high demand for power. With all the growing interest in AI, data centers, I think there's a vested interest in trying making those sustainable. And then the last thing is just that um, we are part of FAIR, which is the fundamental AI research group at Meta. So there's kind of a basic science component to it. All right. When we got our start, we were the Open Catalyst project, and we really focused on seeing how far we could take computing absorption energies. And this is for heterogeneous catalysis. So really the bottleneck there was just being able to run enough DFT. So DFT was really the bottleneck, and the main goal was, can we replace DFT with a machine learning potential that's much, much faster and, if we're lucky, just about as accurate. And we wanted to do this across a huge design space. So not just a single system that we cared about, but across a bunch of catalysts. And I think at the time, this was a bit different. A lot of times people were still training MLIPs on individual systems. So to have models that kind of generalize across a space, we created a large data set. So this is the Open Catalyst 2020 data set. It was large and diverse. At the time, it had about 130 million training examples, so it was big. We've since expanded that more. It required a lot of compute. In addition to the data set, we released, baseline models and a community leaderboard. So that was in 2020. And as time went on, we were interested in some other things. So direct air carbon capture. This was kind of sufficiently out of domain. So we needed a new data set. So create a data set, train some more models. In 2024, we released a data set on materials. Again, kind of a different application or different domain. So we trained more models. You're starting to see a pattern emerge here. And this year we released the open molecules data set, which I'll talk a little bit more about in a second, and a forthcoming open molecular crystals data set. So before I go on, I want to stop and talk a little bit about OML 25. OML 25 probably deserves its own talk, so I'm not going to be able to go in as much detail as maybe some of you'd like, but just kind of hit the high notes. And I mean, this was a big collaboration that resulted in about 100 million DFT calculations. We covered a bunch of different areas. So we looked at biomolecules, metal complexes, electrolytes, and small molecules. And I know there's a bunch of sort of bio enthusiasts probably in this on this call. So I'll talk a little bit more about some of what we did there. So we really heavily sampled PDB. But obviously we're running DFT, so we can't run a huge number of atoms. Kind of the cap, the top of the most atoms that we included were about 350. But we tried to take snapshots of various um, components. So you have like protein-protein interactions, you have protein-ligand interactions. Here it's showing like a DNA protein interaction. So we tried to sample sample the space as much as we could. Yeah, and I think for some of the other areas like metal complexes, mostly single metal centers. Um, with a bunch of, so we have a bunch of, we have a bunch of single metal centers with a bunch of ligands, and kind of randomly sample that space. Electrolytes, we were, again, had kind of a large list of potential anions, cations, solvents, things like that, and kind of randomly selected some, running a bunch of sampling to get different configurations. And then for small molecules, we really leveraged what others have already done. So this is like taking data sets from the literature, recomputing them at the same level of theory.
A very quick interruption. I think
Yeah.
the audio quality is so shitty. We'll just not use the room and we'll use your laptop audio instead.
Okay.
It's better.
Yeah. Wait, am I?
No, you're not on the
Oh, so I actually joined Zoom.
Never mind. Let's try this.
Any better for the folks online? Guess we'll see.
Yeah, let's try.
Um, yeah, sorry. So where I left off is we had just we leveraged a bunch of stuff that had already, like, the community had already generated to make the data set as well. Some other distinguishing features is just the elemental diversity compared to a lot of other kind of molecular data sets. Covered a huge part of the periodic table. Similarly with charge and spin diversity, a lot of times kind of conventionally you've been in this little area here. So being able to go like expand the charge and spin multiplicity opens up the possibilities of doing some new science. Yeah, so I can't do everything justice. There's a bunch of other cool things like reactivity, explicit solvation. I briefly mentioned larger systems, but there's a bunch here, additional properties that we're excited about, but we'll save that for another time. Just wanted to say that this was a big group effort, and it was really fun to work with everybody on this. You know, we've had expertise in kind of like software engineering, which was required to run DFT at this scale. We had the domain expertise, and then we also had kind of machine learning expertise, kind of guiding what you may want to what sort of data you want to train the best SLIP you can. And lastly, it's open source, so you can find it on Hugging Face and try it out for yourselves. All right. So that was the tour. Coming back to the thought here, the thought was, you know, we've generated a bunch of data sets, and the playbook is kind of the same. You know, we generate a new data set, train some models on that data set, and then if it's, you know, if you're interested in new chemistry that's kind of sufficiently out of distribution, you repeat steps 1 and 2. So the question is can we break out of this loop and can we use all the data to train a single model that kind of benefits all application and rises all boats? Okay, so if we take off our chemistry hat for a little bit and put on our machine learning hat, I think there's some really good reasons why you'd want to combine the data. So I think in general, chemistry is, you know, we're challenged with having data. We're kind of in a low data regime. You know, these DFT data sets are super expensive to make. They're also human intensive. So trying to take advantage of as much as we can that we already have would be great. I think the other thing is just that each one of these data sets represents a, like it's very diverse. So each data set brings its own thing to the table. So if we look at these are pairwise matrices. So these are just comparing These are just like the elements 1 through 94, elements 1 through 94, plotting these pairwise interactions. And you can see that for the various data sets, these are quite different just visually. For organic stuff, you have a bunch of carbon, bunch of hydrogen. So you see like about, it's like hot up here, and it's different for other data sets. So what's cool is if you combine them, you get this really rich data distribution on the right. Um, so I think this has been meant to be super quantitative, just sort of illustrating. This is one way to illustrate that there's a lot of like each data set brings its own diversity to the table, and if we can combine them, that can be quite nice from a diversity standpoint. And when we do that, we have a data set of about 30 billion atoms, 500 million, around 500 million structures. I think the one other motivation for this is like why you want more data. If you look at this in the upper right, basically we and others have shown that as you increase your data size, you can also improve model performance. Okay, before we get into new stuff, I want to talk a little bit about an older paper. I guess it's 2024, but it feels older. So this was led by Nima Shoji, who's now a graduate student at Georgia Tech. But this was the first time that we had really tried to train models across different types, like different chemical domains. So we had catalysis, we had small molecules, and we were going to pre-train a model backbone, which we then use to basically we take this pre-trained backbone and we fine tune it on a bunch of individual tasks and see how the model performs on that. So very diverse pre-training followed by specialized fine tuning. Does that make sense to everybody? Um, so this was super effective. And I think I don't want to go too far with this because a lot of these data sets are fairly small. Um, but basically what we saw is that when you compare a fine-tuned, so this is taking the pre-trained base model and then fine-tuning it versus just training models from scratch, there's a huge improvement. Like it's like 50% on average, which I mean that's for people who are doing modeling, I get excited about like a 5% difference. So 50% difference is really huge. And I think again, part of this is probably because this is a large model and these data sets are small. So they're susceptible to overfitting and such. So I think that's part of why you see this really big gain. But either way, I think that the idea that having this diverse pre-training plus specialized fine-tuning, it seems very effective.
Were the pre-training tasks like the same as the fine-tuning tasks, just that you did like all of them?
I mean, they were a little bit different. So during pre-training, we were just doing energies and forces, and some of the fine-tuning tasks were a bit different. Like there's some for QM9 that are not just energy and forces.
Okay.
But yeah, quite similar.
Do you have tasks where you can compare like how well does the pre-training model do compared to the fine-tuning?
Oh,
What's the fine-tuning?
yeah, so we didn't actually evaluate the base model on the tasks, and I think part of that was because we didn't really focus on that performance at all. We didn't want to. Yeah, at the time I was thinking, oh, we don't want to fit the things. Like we just want to train this really good trunk. But I think that leads into the next point, which is like, um, this was kind of a proof of concept to see if we could train these things. Because again, I think it's still not well understood. Like these are different levels of DFT theory, so you're kind of mixing these things, and I think that makes a lot of people a bit uneasy. So trying to understand if that was possible. So this was a proof of concept, but to your point, Felix, just it required specialized fine tuning, which is not ideal because for every task that you're interested in, you have to go specialize that model, and so I think it's still better than training everything from scratch for sure. But I mean, it'd be nice if you didn't have to do that. So that was one of the major shortcomings of this. Any other questions? Okay. So moving forward, this kind of led to the universal model for atoms or UMAS. And the idea here is just to have a single model that works out of the box for molecules, materials, and others, and without this need for specialized fine tuning. And we wanted the model to work across a bunch of things. So molecular dynamics, TFT relaxations, vibrational analysis, Monte Carlo simulation for generative models, etc. In order to really do that, though, we needed to, like, our team hadn't focused on some of these other applications. So we wanted to spend some time designing a model specifically for physical property prediction, so molecular dynamics, vibrational analysis, things like that. This resulted in ESEN. This is ICML this year, and this was led by Shang Fu. So the main idea here is just that, you know, a bunch of models that had been developed by us and others may did well on some val and tests. You can see on the right, but then on other applications that you care about, like NVE, molecular dynamics, they don't perform well. So this paper was really trying to dive into that and look at the different architectural design choices that were made and understand how some of this stuff would manifest. And I would say that one interesting thing that came here is just that having conserving forces is a requirement, but it's not sufficient actually to have zero energy drift. So that was interesting. Okay, so yeah, again, this paper really dove into different architectural design choices that were being made and kind of did, yeah.
Say having conservative forces also if you have conservative forces, it's necessary. But do you think this implies that we need some architecture choices that make that happen or that make that possible? Or yeah.
Like, you mean without doing the actual taking the gradient?
Yeah.
I mean, it'd be awesome because for all the people that were working on these models, these direct models, I mean, there's a reason. It's because yeah, it can save you a lot. It saves you that second backprop, maybe 2x, and then you need to use a reasonably high precision. So if you're using lower precision, which a lot of people are in training, you can't do that if you're doing gradient-based forces. So you can lose quite a bit. It can slow down things quite a bit, but I think people are certainly thinking in that direction. I think maybe Orb V3 had some ideas on how to they added some loss term, I believe, to partially enforce conserving forces without maybe spending all of the time. But yeah, I mean, it would be nice if someone could figure that out. That would be excellent. Any other questions?
So yeah, I think the thing that you mean in orb is just this equigrad blocks, because they don't have an equivariant net.
Oh, I see. Oh, so that's just for rotations, and I see.
Yeah.
Okay, so they didn't actually. So they had to do. Yeah, I guess then no one has figured out a way to not do that. Take the second backwards.
Well, which is maybe also something interesting to talk about, that you have this ASAN equivariant thing and make a big deal out of what's it called? If you train multiple, if you do sharding, mixture of experts.
Oh, yeah.
And then you have the equivariant mixture of experts, and it needs a linear mixture of experts, and then ORB just has a non-equivariant model, and it seems to work pretty good as well. Oh, just as well, I don't know.
Yeah, we can maybe. I'll get to the mixture of linear experts, and maybe we can talk a little bit more later just about some of the larger design choices that people are making in the field. And I can maybe give some rationale for why we chose what we did. Yeah. Okay, so as part of the ESEN paper, I mean, if you haven't read it, check it out. It's really thorough in the different design choices. So that's fun. And I think the good news about this is that, as I mentioned at the first slide in this, basically you were seeing models do well on valid tests, but not do well on some of the physical property prediction tasks that you cared about. So what this paper showed is that if you follow some of the design choices, valid tests correlate with these physical properties that you care about. Yes.
So on the right, you run some simulation and then you look at the diversity and that's some entropy, or how does it work?
This is for, sorry, I think this is a phonon task. So
Okay,
it's something
so
about, yeah, it's about phonons, and I think um, basically, yeah, this is just a physical property that, again, we're
how
just
do you
trying to show.
obtain it? By running some simulation?
Yeah, basically, I think you run a bunch of simulations and then you do, so you get a bunch of forces from your simulations, and then you do, someone help me out here. You're taking, yeah, exactly. Thank you. Yeah. Exactly. So you're not taking the necessarily like the second derivative. It's just you're doing numerical integration basically from the forces. Yeah.
For this data set, do you have any calibration against actual experimental measurement of the properties that are being predicted?
No, I think these are all computational properties. Yeah. Which I mean, that is like the goal for sure. But a lot of what we're doing is also trying to match, like our MLIP should match DFT. And I think there's a little bit of a question of like, does DFT itself match experiment? And then you get into this chicken and the egg sort of thing. So I think for a lot of the benchmarking we've done for now, it's just like we're trying to make a DFT surrogate. Let's check that. And then I think what you're talking about is like the next step. Yeah.
Okay, like valid tests, you're just measuring like the regression loss on the forces.
Say that again.
You're just measuring like what is the error in the forces that you.
Yeah.
And then these other properties are like, if I now like take this force field and integrate it and get some other stuff.
Exactly. Yeah. And so I think the problem with like what I meant by this slide is just that when you so calculating some of these is more intensive than just checking like the MAE of your forces. And so you don't want, like, as you're doing model development, you don't want to do that every single time if you could avoid it. It gets really cumbersome. So that's why if these correlate, that's kind of good news for all of us doing model development, because then you can trust, you're not flying blind. Yeah. Right here, Tess? Or,
Sorry for the K.
this is thermal conductivity. Yeah. Yeah.
So when you're comparing photons, you're measuring.
I think we do. Yeah, you'd have to ask someone else on our team who actually computed those, but I think we have both. Like there's a number of things that we do now for phonon related. Yeah.
So does no one like try to weight the loss so that you account for like your integration error rather than just like
I think,
instantaneous?
yeah, I think people have tried to do that, but again, it's really cumbersome. Like I think there have been a few papers on that. I think maybe a DT's group from Berkeley tried to add something to the loss based on like, if you care about MD, I think they were looking at like the densities or something like that and trying to incorporate that into the loss. But it's much harder to do for sure. Yeah. Okay. So takeaway from this is that again, now our valid tests correlate with the physical property predictions, which is great. And for us, it was also good because we settled on our architecture for UMA. I would say some of the differences are kind of in a typical MLIP, the inputs are 3D atomic positions and the atom types. For UMA, we add a few more, which is the DFT task. So if you care about, let's say your input is a material, then your task would be OMAT. We also optionally include charge and spin. This is mostly for molecules. All right. At this point, we have a large data set. We have a model, but how large of a model do you actually need to fit the data? So to look into this, we took some inspiration from other ML domains and looked at scaling relations. So what you're seeing here is an isoplop curve, and this is basically just means constant compute. So each one of these lines represents constant compute. So you have active parameters and the loss. So if you increase the active parameters, you have to decrease the total amount of data that it sees to have like constant compute. What you can do from this is then you can fit these minima and look at some compute optimal training regimes. So you can see this is the fit. If we squint a little bit, do some extrapolation, we estimate that we need about a 700 million parameter model to fit our data set of 30 billion atoms. And this is considerably bigger than models ourselves and others have been training. So I think a natural question that comes up here is some of the earlier models were already slow. And if we're going to make this, 7 times larger, it's going to get even slower, which is a problem for a lot of chemistry applications. We want models that are actually fast. So what can we do about that?
I just asked in the last plot so I guess like maybe you can compare the number of parameters with like say the number of parameters language model, but like how does that compare against two?
It's orders of magnitude lower than like the LLM training. Yeah. Okay, so to kind of address this, we need large models to fit the data, but they're slow. We introduce the mixture of linear experts, and this is also kind of taking inspiration from some of the things in LLMs. Although what we're calling MOLE is definitely different than kind of a traditional MOE. So I guess the idea here, though, is to increase capacity without sacrificing speed. And for us, sacrificing speed is on the inference side. So we're going to slow things down during training, but speed it up. Yeah.
I thought purpose here was to be able to choose between different tasks and not something related to speed or capacity.
Oh, it's not just, yeah, I think I don't think we know exactly what the experts are learning, but I don't think that the experts are just for a specific task from what I've seen.
Didn't you have some figure where you show like performance with an equally sized model that doesn't use mixture of experts?
Yeah.
Just much worse at the different tasks.
Yeah, I mean, I think it definitely helps for that for sure. But like, I don't think I don't think that the number of the experts map directly to tasks. So give me a few slides and then we'll come back to that. Okay, so in our model, we do some edgewise processing, and the biggest part of this edgewise processing is the SO2 conv, or ESN convolution. And this is just a set of linear operations. So basically, each one of these linear operations gets replaced with this MOLE layer. And these are just a linear combination of the expert weights. So we have this router that determines our expert coefficients. Then we compute W star and you do your linear operation. So the global embedding that goes into this, it depends on the atomic composition, the DFT task, the charge, and the spin. And what's nice about that is none of these change throughout a simulation. So if you're going to run MD on or any other process where you run a bunch of sequential steps, usually these don't change. So what's cool about that is we can pre-merge these. So that's where you get the speed up during inference, is you can pre-merge these weights, the expert weights, and then the model compresses down to it's much smaller.
So that again shows it doesn't have more capacity, right? Because like it's an equivalence. You just like everything is linear, and so you don't have more capacity, but you have now the ability to choose between different weights for different tasks because you have to go with that.
I guess it depends a little bit on how you're thinking of capacity, but for if we just train a single task model for each one of these tasks, this is a normalized performance for the energy. Now, if we train a naive multitask model, same size, it's worse. It has worse performance. If we add MOLE, then we're better than the single task performance by itself. So the MOLE is kind of unlocking us to be able to train across these different tasks and beat the single task performance. This is for smaller model sizes. This is less true as you get to larger and larger models. So this, to me, the way I think about it is you're adding capacity to these small models in a specific way that'll allow you to do some task specific things that improves performance. Does that make sense, Hans?
Cool.
Okay.
These three are like constant number of parameters or like
Constant number of
similar
like
different
it's constant number of active parameter equivalents. So they all basically have the same active parameters.
Yeah, the difference time after you merge the matrix into one.
Exactly. Yeah. But I think we're saying like active parameters is a nice way. Like I think a lot of people can understand it through the way people talk about MOEs, but technically all the parameters are active because we do this linear combination. But in terms of compute, the real way to think about it is how much like how many flops are being used. One other thing we looked at is just like the convergence with the number of experts. So, you know, one way to think about this is we have 5 tasks in pre-training. And so if, you know, if only a single expert was learning a given task, maybe you wouldn't see these higher numbers be effective. But basically from dense to 8, you see a big gap. From 8 to 32, there's a smaller gap. And from 32 to 128, there's not much. So all of our MOLE models use 32 experts.
So you have like multiple layers where you have different experts.
Yeah.
And then
At each message passing layer, basically.
and for each of these layers, you choose a different subset of experts.
No, so these coefficients
Yeah.
get chosen once at the beginning because none of these change.
But are they the same for every layer or are they different? Like is the number of alphas like
The alphas,
k times the number of layers or
No.
it's just k?
yeah, just kidding.
So it's not, you don't actually get like a combinatorial thing where
How do you prevent a hive mind? How do you stop all the experts from learning the same thing? Just random.
We didn't do a lot to prevent that necessarily, but we looked at some of what they're learning, and it seems like it's like not a ton of them are like going to zero. We were kind of doing a little bit of analysis on these expert coefficients and just seeing what happens with various data sets. Yeah, but it doesn't seem to collapse.
But it could be like ensembling a little bit versus like
Yeah, I think it's hard to interpret some of exactly what's going on, and we could probably do some more analysis, but I think it is a little bit hard to interpret exactly what's being learned by each one of those experts.
How many is typically on at this time?
But I mean, like all of them are on in the sense you just have your alphas that are sum up to one, I think.
Exactly.
You don't encourage sparsity on this.
No, you just turn them all into a single matrix by summing them up.
Yeah, you just basically get this W star here, like exactly what Hannes was just saying. Like this is just a linear combination to get this. So technically they're all on, but these, you know, these coefficients decide how on or off each expert is.
If you look at statistics of activations, are there any trends?
We haven't done a ton of analysis, but I mean, it does seem like there's some, I should have put it on here. maybe we can dig it up at the end. There's like, we did some, for each expert, we plot like a periodic table. And so we look at like the pairs and see kind of what like lights up. And there was some interest. I don't know. I think it's hard to interpret. I wasn't able to like pick one thing and say like, okay, this is definitely what's happening. But I would also say that like in LLMs, I think people have tried to do a lot of interpreting what specific experts are doing. And my understanding is they can't do that. Like they just, yeah, it's hard to do.
I think just look that it's a linear picture of expertise.
Yeah, that's true. I mean, yeah. Okay. So now that we've introduced MOLE, I want to come back to scaling relations. And I know that this is a lot visually, but we kind of talked about the ISO plot, plots on the left, and now we just have dense versus MOLE. And I think what's really interesting here is that there is a delta between your dense and MOLE. So at a certain size, this diminishes as we get larger and larger. And we have some hypothesis for what might be happening there, but kind of in the regimes that we're interested, you basically need a 2.5 times larger dense model to match the performance of the MOLE model. And what we're doing here is we're just kind of playing this speed and accuracy trade-off, right? Because I said, we need a certain model size or certain capacity to fit the data, but we all want fast models. So I think really that's what we're playing with here. And even then, you can't really do it all with a single model. So we did train a series just so they kind of fit different applications depending on the accuracy or the speed that you need for your particular application. There's not any big surprises here, right? Like the number of inference calls you get decreases with the model size. The number of atoms you can fit on a single GPU decreases with model size. Our small and medium models are both conservative. We didn't, our large model, it's really hard to train a 700 million parameter model with that, the gradient based forces. So this is direct force and more of just, we wanted to see how that model performs as sort of like a proof point. The hypothesis had kind of been, you can train a single model, but how does it actually perform? So I'm not gonna actually, before I move on, I won't drag through a bunch. We have a bunch of tables and stuff like that in the paper. You can go look through those. So I won't drag you through all the performance, but I think the TLDR is just that kind of surprisingly, the model is on par or better than state of the art across most of the things that we tested, just with a single model. And that's surprising again from some of the previous experience we had with JMP. I sort of expected that there would be some amount of fine tuning that was required to really have a great model, but it seems like that with MOLE, that's not necessarily needed. Just to highlight a few performance things, our team had been chasing catalysis for quite a while, and in particular trying to reach 0.1 EV absorption energy. So that was kind of the target here, and these are actually over time. So we were making progress over time, and then with our recent release, we finally kind of broke that threshold, which was exciting for us. I did put a little star here because while the model is good, we also changed our approach slightly. So I think it's the change of the approach plus the model that resulted in this. It's not just the model itself.
So here the task is you have your slab of some metal or something.
Yeah.
And you place something in a random position and then you evaluate the energy, then you run a relaxation with your model, and then you evaluate the energy and then you look at the delta and see if that's the right one.
Yeah, it's something like that. Instead of, so we have your absorption energy is equal to like the add slab. So this is like the energy, the relaxed energy of the adsorbate on the slab minus the slab itself, also minus the adsorbate. But
Okay, so it's not a quantity that's related to any type of simulation. You just evaluate one structure.
It actually, so technically the absorption energy it's a global optimization. So you like it shouldn't be just a local
So
optimization. So you should do a bunch of these things, but
you initialize and make
exactly. You can-
positions, then minimize, and then you look at the minimum energy.
yes, and there is like that the lowest energy you get that's like actually valid. That would be your absorption energy. So we have a real task called absorb ML where we do the global optimization. And yeah, with the UMA models, they're better than anything else that we've seen. I think the highest we got is like 74% success. So that's like without any DFT at all. And that's, yeah. So I think that's pretty cool for us. That's been something that we've been interested in a long time. So, but I think there is a little bit of an asterisk because a lot of these other models, they directly predicted the absorption energy, where with this model, we're computing the total energy and kind of doing each one of these steps. Another result is just, I think MapBench Discovery has kind of been a popular leaderboard in the community, and we wanted to make sure we didn't regress there. So the UMA medium model is basically on par with this specialized ESIN model that's on top of the leaderboard right now. For molecules, we have a bunch of benchmarks. I've only highlighted a couple here, but I think for biomolecules, especially for small drug-like molecules, we see that the accuracy of the models is really good. Like torsional degrees of freedom, things like that. Us and others have seen that the models are really quite good. We've also looked at for electrolytes, I have this anion OOD. So this is an anion that was held out of training. And again, the accuracy there is quite good. So I think that's promising in terms of generalization. Similarly for metal complexes, these are experimental based complexes that were not in train. I think the target accuracy, I'm not sure, maybe some other people in the audience could have a better idea of what the accuracy you'd want here is. Maybe between 2 and 3 kcal per mole, I'm not sure, but I think given the diversity of metals that we include here, I think it's still quite a cool result. All right, one last thing to show you guys. So I think there's a lot of questions on whether or not you should be training on diverse data across domains. One cool result is that data is this really effective regularizer. So if we look here, this is for a large model. So these are all dense models, but they're large. So these are 700 million parameter models. And you can see the large models trained on the single tasks. We're normalizing for that. It's a little bit hard to see on the energy one, but I think there's at least one data set where you do start to see overfitting. On the forces, you really start to see overfitting in a bunch of them. So the models can definitely are expressive and can overfit on these data sets. Now, when we train in a multitask setting, we reach pretty similar levels for energy. Sometimes it's better, sometimes it's slightly worse. But I think the cool thing on a lot of the forces too is that we prevent a lot of the overfitting. So I think that's a neat result for using very diverse data. Okay. Oh, so a fun result. Oops. Fun result is we have 2 different copper complexes here, and I think they start in the same geometry. If you set their charge and spin differently, they relax to different geometries, which is what they're supposed to do. But if you, like a lot of times, MLIPs didn't take charges and spin as inputs, so this wouldn't have been possible. So the fact that they go to the right place is quite cool. Anecdotal, but cool. Another one here, for those of you interested in batteries, ethylene carbonate is a super common electrolyte molecule. that I think is involved in SEI formation. So you can see the neutral one just sort of jiggling around, where if we have this radical anion, you actually start to see the ring opening happening. Okay, so kind of wrapping it up here, I think data is really key. And with more data, we can build more capable models. A wide data distribution, it encourages generalization and does prevent overfitting. A sub point here is that we are still data bound, so we could train larger models. It's just that we don't have enough data for that to make sense. I think there's a question of what the target accuracy actually is in various domains, and that's something that we and others are trying to work out. But if you do need much more accuracy, we're going to need more data. Lastly, it is possible to train a single model that achieves strong performance across domains and various benchmarks without the need for specialized tuning. Okay, now that I've said a bunch of nice things about the model, what are some of the limitations and weaknesses? One is long-range interactions. So our model is just using kind of the standard 6 angstrom cutoff. The receptive field is much larger based on message passing. Information is passed at long range is pretty open question. There's a lot of people working on this right now, so I imagine that's something that's going to be improved. The way that we handle chart and spin is a bit naive, so I think that can also be improved. I wanted to talk about outliers because I think this one's pretty important depending on what you work on. If you're doing large screening campaigns, maybe the model doing something weird 1 out of 1,000 times isn't that big of a deal. But if you're looking at like crystal structure prediction or something else like that, maybe it is a big deal. So I think from what we've seen, these models still have outliers, and that's hard to control. So it would be really great if we could have uncertainty quantification that's not just meh, I don't know what to do, let's do an ensemble. And yeah. Also, I think they can always be faster. I think we're quite limited right now. If people, especially in the biospace, if you want to do larger atomic systems, it's still, we're still a lot slower than classical potentials. So I think there's room for improvement in here, other ideas. And lastly, just others that hopefully that you all help us find. So if you play with a model and you find something, please let us know. And you don't have to take our word for it. You can try the demo that's on Hugging Face. You can upload structures and try it for free there. Otherwise, you can also install our library, which hopefully you can do with just a pip install and run your ASC calculator. All right. With that, thank you guys. And if you have any questions, we can spend some time chatting now.
So I'm more from like the LM side of things. Do you use any of the like techniques to speed up inference there for like chemical modeling, so like distillation, quantization, classification, speculative sampling, all these?
Yeah, some of them we can't use in our domain, unfortunately, like trying to go to lower precision. We do that during training, so I didn't talk about some of our innovations on the training side, but we definitely, so we have a multi-stage training where we use lower precision at the beginning, and really try and, speed things up and then kind of finish with FP32 and so on and so forth. But yeah, so that's precision. Distillation, I think distillation is super exciting. We didn't spend a whole lot of time thinking about it ourselves, but I think that's one thing where the community can get involved and engaged and do some interesting work.
I guess you mentioned this, but yeah, I was curious about how you are handling the charts and how you're calculating these as well.
Yeah, so we're not calculating them. They're inputs to the model. So it's like, if you're gonna, I don't know, did you run molecular DFT? Okay. But like when you run like Orca or Gaussian or something like that, you set the charge and the spin. So I guess you use our model in the same way, essentially, like you set the overall charge, the global charge and spin.
Oh, but it's the, you're not giving it some like density.
We're not doing like partial spins and
Okay.
partial charges. Yeah. Although that like with open molecules, we are trying to release that data, and I think that that's an interesting target or things that people will probably use in the future.
Can you do magnetic rings with the relaxation?
I don't know that we can, but I think that there's like interesting possibilities there too. Like some of the stuff that we do test for materials is a bit like actually anything but molecules is a bit strange, right? Like the way that we embed these, we just basically say anything that's not molecules, you have anything periodic is charge 0, like global charge 0, and then the spin we give it a null token, so it just like no information essentially because it doesn't work the same. Yeah, but I think there's a lot of room there to do cooler things on the material side for sure. Yeah.
So Shripping has work on matchness, which simply shows you can downsample almost 4 to like 400K structures. And not only does it the model see roughly as good, you know, put scare quotes on that if you want to, but it also seems like they're more stable. What do you okay, scare quotes wherever you want, but like what do you make of that? What do you think that's telling us like about the how much data do you really need? Because this is kind of a kitchen sink to data, right? Like is less data better sometimes? Is that highlighting architecture problems? Like, what do we learn from that?
I don't think less data is not better. But I do think that like the amount of data that we have and we've used here, like you can, I'm sure in many cases you could reduce, like you could train on a much smaller set and get like close to similar performance, especially for data sets where you have like OC20, where you have relaxation. So anything relaxation based, these are super correlated. Each frame is very correlated. So yeah, I think you can definitely you could train with less data, but I think the idea that less data is good. Yeah, I don't agree with that. I just think that it's a question of
What did you say was better? This thing.
I mean, my understanding from reading the paper, which you know maybe I'm might be misremembering, but their models are more stable. They train on essentially like they pull out 400K structures with like different sampling, and the idea is that you're sampling more evenly over the space, so you get the interpretation is like you're doing some regularization of the data selection potentially there.
So, and more stable means that simulations don't blow up.
That's right.
So simulations will blow up.
they don't, but yeah, I mean, I think the thing is though is you can we there's a lot of questions around data that we don't know the answer to, but I don't think the right conclusion is less data is better. Like there are a lot of things we don't understand. So like when you train on OMAT and then you fine tune on like MP Traj and SLX, those are really like OMAT has really high forces, where these other ones are more relaxation based things. So the forces are much lower and you get over smoothing of the potential surface. So you get like you start to see in the ESENT paper, I think there's some examples where like for specific photon bands, like you can just see that the model is over, like it's smoothing when it shouldn't be, like it's not as sharp in places that it should. And I think there's a lot of questions around data for sure, but I don't think less data is the answer. Yeah.
What are the practical applications where these models are now good enough to replace some existing technologies or enable new things that cannot be done with computation?
Yeah, I mean, I think two exciting ones that I'll say, like these guys can maybe comment on this even more, but I think for molecules, like any like torsional barriers you're looking at just feels like they're really, really good for that. So I think that's interesting, or that's a good one.
And can you go a step further? Like, what does looking at torsional barriers help you do?
Sure. One practical, so one of the evals we made for open molecules is called strain energy.
Yeah.
And the point of that is to try and help researchers understand like if they put a molecule in a pocket, how strained is that configuration? or like how strange is that molecule in general. And that, from my understanding, people doing drug discovery will use a metric like that. And if it's as good as it is, then that should enable some new science.
Okay.
And then I would say the other one too is just MLIPs have not been good on metal centers. So like metal complexes in molecules, like there just hasn't been data. So having something that can actually go across there is quite interesting. And some of the little anecdotal results I showed you, I think are cool. I think it's all relatively fresh, so we're trying to get our heads around what is actually possible at this point as well. Yeah, and the absorption energy one. The absorption energy one, that's really cool for kind of your transition.
What's the comparative speed up to if I run my enzyme simulation now with DFT versus with your model?
I guess for an enzyme simulation, like a bond is breaking and forming, with something like that. I would say that you can't do that without quantum mechanics. And so you have to run DFT basically. And so that's, I mean, 10,000 times or more faster. Yeah.
Okay, so
Because the classical potentials are fast, but they can't break bonds. So they couldn't do.
no, yeah, I'm saying we run one step with DFT and one step with your model.
Yeah.
What's the speed comparison?
Oh, for that one, let's say 10,000, but I think it really varies on, like, if you do something that's really small, like a really small molecule, something that only has a few atoms, like
The speed up is less.
much less. Yeah. So it varies quite a bit depending on the size of the thing that you're working on.
Then maybe last question about
Yeah.
Scala. Like this, can you say a few
Scala.
words about Scala?
Um,
What is it?
yeah, what is it? Well,
How does it compare to your stuff?
it is quite different. Like I would say they're pushing in a different direction. Like they're trying to make DFT actually better. So they're trying to make DFT more accurate and better. So I guess the analogy would be, if we make another huge data set, maybe and use a different functional based on Scala or something like that. Yeah. But I think they're trying to push really on the accuracy of DFT, because obviously DFT is not perfect. There's much more expensive methods like CCSD, and they're trying to approach that accuracy with the cost of DFT. Yeah. Yeah. Did that make sense?
Yeah.
Okay.
All right. Thank you.